This course, as I have told you, is EE 110N. This is Introduction to Electronic Circuits. In the first lecture, we shall introduce the course, and we shall also introduce some basic electrical quantities. This is my name, and we plan on about, as I said, 40 plus minus 2 lectures for covering the total material. This course shall deal with basically circuits and devices, electronic circuits and devices. And to be able to do justice to electronic circuits and devices, we shall first study about 16 lectures will be devoted to general circuits, and then the rest of it, that is 24, shall be to devices plus circuits containing electronic devices. This will be the usual, this will be the general breakup, about 16 to general circuits and 24 to electronic devices plus circuits containing electronic devices. To be able to follow the course, we must understand what these terms mean. These terms like device, a term circuit, and then often there shall be a term called system. We should also understand what is electrical engineering. At least have a broad idea of what is electrical engineering. Well, electrical engineering is not your major discipline, I understand, right? Is there anybody belonging to electrical engineering here? No. Okay. So it is all the more important as to what electrical engineering means. Double E basically deals with two kinds of phenomena. One is related to energy and the other is related to information. The energy aspect of electrical engineering is concerned with generation, transmission, distribution and utilization of electrical energy. Usually high power energy, that is the electrical voltages and currents that shall be dealt with in consideration of energy are usually high amplitude ones. That is, you would not talk of, when you are considering energy aspect, you would not talk of a voltage like a 0.1 microvolt or 1 milliampere current. You will talk of currents of the order of amperes or 220 volts and so on. The energy aspect has to do with high amplitude voltages and currents, and they are concerned with generation of such high amplitude electrical quantities, generation at a particular point like the Indraprasth power station, then transmission from a power station to another, let's say, substation like the RK Puram grid, and then generation, transmission, then distribution to various houses, for example, and utilization of this energy for lighting, for heating and for many other purposes. This is the energy aspect, whereas the information aspect of electrical engineering deals with low amplitude. These are usual and broad definitions. They deal with low amplitude voltages and currents, and usually they would be of the order of a volt or less, currents of the order of a milliampere or less, although power also is important, but the power level in generation, transmission, distribution and utilization of information containing electrical signals or electrical voltages and currents, the energy level or the amplitude level shall never compare with the levels of energy and currents and voltages which are relevant to the energy aspect. So, these are usually low amplitude electrical voltages and currents. Now, the information aspect is of course most important in communication, any type of communication from one place to another, from one human being to another, or from a group of human beings to another group of human beings, and this is done through electrical signals. So, communication is the main let us say utilizer of the information aspect of electrical engineering, and this communication is done with the help of what we are going to study, namely devices and circuits. Broadly, a device is a building block for a circuit. For example, a transistor is a device, a resistor is a device, an inductor is a device, a capacitor is a device, a diode is a device, and there are many other examples. An integrated circuit, a chip, is a device, and so on and so forth. And a circuit is a meaningful interconnection of devices, a meaningful interconnection. Well, you could put a resistor here and a capacitor here without any connection between them. Well, that does not make a circuit. A circuit is a meaningful interconnection of devices to perform a specified function. Otherwise, it is not a circuit. A circuit can be of two types. Circuit can be lumped or distributed. These are all new terms, and therefore you should pay attention to their meanings and interpretations. When a circuit is so small compared to the wavelength of electromagnetic phenomenon, when a circuit is small compared to the wavelength of the electromagnetic phenomenon, then the total electromagnetic phenomenon can be considered to occur at a point in space. In other words, when a circuit is of small dimension compared to the wavelength, the whole phenomena can be thought to be lumped at a specific location in space. So, the space variable x, y or z, they are not important in a lumped circuit. Such circuits are said to be lumped. In other words, the voltages and currents shall only be considered as functions of time t. The space locations are not important. On the other hand, if the circuit is so large that its dimensions are comparable to the wavelength of the electromagnetic phenomena, for example, a transmission line, you generate power at Indraprasth and maybe you transmit it to some point in Madhya Pradesh, or from a Madhya Pradesh grid you borrow some power for Delhi. The length of the line is comparable to the wavelength, and therefore that circuit is a distributed circuit. In this particular course, well, in a distributed circuit, you see voltages and currents in general shall depend on the space coordinates and also time, and therefore in general there shall be functions of x, y, z and also time. Alright, x, y, z are the space coordinates and t is the time. In this particular course we shall be concerned only with lumped circuits. We shall not consider distributed circuits at all. But it is good to know that distributed circuits do exist. Then you shall often get a term like system. We have already said what is a device, we have already said what is a circuit, and then you will also get a term like system. Now, a system consists of devices circuits, well, circuits are meaningful interconnection of devices, therefore a system contains circuits, it contains devices, but now devices can be electrical as well as non-electrical or interface devices. For example, a public address system, when a political leader speaks to his electorate, well, it is not a public address circuit, it is a system, because he speaks in front of a transducer which converts sound energy or mechanical energy into electrical energy. Now, a transducer, a microphone, is not purely an electrical device, it is an electromechanical device or mechano-electrical device, all right. So, a system consists of circuits and devices, where devices may include electrical as well as non-electrical and interface devices. A public address system has a microphone which is not purely an electrical circuit or device, then it contains an amplifier which is in fact a circuit, amplifier is a circuit, then the amplifier goes to a loudspeaker which is also a transducer. This is not a purely electrical device, it is an electrical energy conversion to sound energy or mechanical energy. Now, such a conglomeration of circuits and devices, the only difference is devices may contain non-electrical or interface devices also. Then the total conglomeration is called a system. For example, a public address system is an example of a communication system. There are other types of communication systems and so on. So, the word system should be familiar to you. Then we shall also use the word model in many situations. A model in electrical engineering terminology is quite different from the dictionary or the popular use of the word model. A model is invariably associated with an adjective circuit. It is a circuit model. Okay, a circuit model is an equivalent electrical circuit for a physical device. A circuit model, or simply a model, in the context of electrical engineering or electronic circuits, a model shall be used to mean a circuit model, and a model is the equivalent circuit of a physical device. A physical device could, for example, be a transistor. And as we shall see later, if the current, there are three terminals in the transistors, base, collector and emitter. We shall see this in details later. I am just illustrating a point. If the current in the collector and the base are given by I sub C and I sub B, then you will see later that a small signal equivalent circuit shall be simply like this. A resistance R pi and beta I sub B, this is the collector current I sub C. Now, this is not the physical device. The physical device is this. This is a schematic symbol for a physical device, and this one represents the performance characteristic with some approximations of the physical device. So, this is called a model. All right. To take a simpler example, let us consider a resistance. Let us consider a resistance. Have you seen a resistance in the laboratory? A resistance? Yes, you have, with color codes and all that. All right. Take a simple resistance. Now, if you measure, if you put a voltage generator across it, V, all right, and measure the current I. Now, this V can be of any frequency. In other words, the frequency of the voltage source is a sinusoidal source for simplicity, let us say, whose frequency can be varied. So, omega, that is, it is of the form Vm sine of omega t or cosine omega t. It is a sinusoidal signal, all right, sinusoidal voltage. If the frequency is varied and you measure the ratio V by I, all right, then one can show that the variation would be like this. I beg your pardon, I have made a mistake. Let me use some other color. One can show that the variation would be like this. If you measure the ratio of V by I and vary the frequency, then it is like this. And then you see, this is the characteristic of the physical device, the resistance as we call it. And you can see that over this range, which we might call A, V by I is a constant, so it behaves as a pure resistance. Over this range A, it behaves as a pure resistance, and therefore this is a model for the physical resistance in this range A. In this range B, let us say, the V by I increases with frequency, and as you shall see later, this part can be characterized by a resistance in series with an inductance. The impedance of an inductance, do not be worried about these terms, we shall define, explain later, but over a certain frequency range, the model, no longer a pure resistance model suffices, we have to include an inductance. And over the rest of the range C, it appears that we have to include a capacitance across the resistance and inductance. So these three are examples of models of a simple device like a resistance that you see in the laboratory. If you make a physical measurement of this at various frequencies, then the model at various ranges of frequencies shall be different. And this is what we mean by the term model. All right, then let us go back to some basics like physical quantities. We will start with force. We will, these are very relevant to electronic circuits. Let us review some of the concepts that you must have already learned in mechanics and also in electricity and magnetism in the JEE syllabus or the first year physics course. This is just to refresh our memory about these various quantities. Force, as you know, is defined with Newton's second law of motion, right? Force is a vector. You are acquainted with vectors and scalars? Yes. Force is a vector given by m times acceleration, mass times acceleration, and the unit of force is 1 Newton in International System of Units, SI units. 1 Newton is a force required to generate an acceleration of 1 meter per second squared to a mass of how much? 1 kilogram. All right. So the unit of a force is 1 Newton. Energy is expressed in joules, and energy is the capacity for doing work. If 1 kilogram mass moves with a velocity of 1 meter per second, then it has a kinetic energy of half a joule, 0.5 joule. Okay, so the unit is joule. You can have many other ways of defining a joule, but this is good enough. Power is the rate of doing work. So if energy is denoted by W, then power P is equal to dW dt, rate of doing work, and therefore the unit should be joules per second, which we call a watt. All right. Now charge. Charge is usually defined in terms of newtons. That is, you place two charges and express the force of attraction or repulsion between them in newtons. All right. But charge for electrical engineers, for electrical engineering and electronic circuits, we shall conveniently define, is not an absolute definition, we shall conveniently define in terms of an electron. As you know, an electronic charge is 1.602 times 10 to the minus 19 coulombs. And so 1 coulomb can now be defined in terms of the charge of a certain number of electrons, and this number is 6.24 times 10 to the 8 electronic charge, 10 to the 18 electronic charge. You can also describe 1 coulomb in terms of the force experienced by a charge. Okay, you know the force experienced by a charge is given by the charge multiplied by the electric field QE, and therefore a coulomb is that amount of charge which experiences a force of 1 Newton in an electric field of 1 volt per meter. All right, you can define that way, or you can also define a charge in terms of a current. It is the amount, 1 coulomb is the amount of charge transferred by a current of 1 ampere in 1 second. And this brings, we are not making absolute definitions, these are convenient ways of looking at these various quantities. Absolute definition you look in the physics course, how to measure absolute measurement of charge and current and all that. This brings us to the definition of a current. Current I obviously is the rate of flow of charge, that is dq dt, and the unit should be coulomb per second, which has been named after Ampere, the great electrical engineer, and the unit coulombs per second is given the name of Ampere. Now in considering current, since current is related to flow of charge, we must distinguish between the polarities of charge. Suppose we have an electric field in this direction E, and you have a positive charge, let us say Q1 plus, and a negative charge, let us say Q2, which is negative. All right. Now then the positive charge shall move in which direction? In the direction of the field. It shall move in this direction, and this shall move in this direction. The current then shall consist of two components, one due to the motion of positive charge, the other due to the motion of negative charge. Now a negative charge moving from right to left is equivalent to a positive charge moving from left to right, and therefore the current here shall be dq1 plus dt, that is from left to right due to the motion of positive charges, plus dq2 minus dt. It contains two components, one due to positive charge, the other due to negative charge. This shall be useful when we consider the electronic devices like a diode or a semiconductor transistor, where there are carriers, charge carriers of both polarities, positive as well as negative, and therefore we shall have to consider both the components of charge, of current. One should also recall the definition of potential, because voltage is basically defined from a potential. Potential, electric potential at a point in space is defined as the amount of work required to be done to bring a unit positive charge from infinity up to that point. All right. And potential difference between 2 points, let us say what should I use for, let us say phi 1 and phi 2. If these are two absolute potentials of the 2 points, then phi 1 minus phi 2 is called the potential difference between these 2 points or the voltage between these 2 points. And as you know, for measurement of voltage, voltage is basically difference of potential between 2 points, and it becomes absolutely convenient if we can fix a reference potential, and the reference potential is that of the earth, not this earth, the earth down below. It has to be the conducting earth, all right. That is considered as zero potential, and therefore all potentials are considered as voltages. But you must remember that voltage is indeed a potential difference, and therefore if you have a reference, when you say the line, the overhead line is 11 kV, that means taking the ground as zero potential, all right. This must be understood. It should also be understood that if potential increases, let us take 2 points, if potential increases in this direction phi, that is, let us say this is 10 volt and this is 0 volt, all right. Potential is also expressed in volts, okay. This is the reference, and this is, if potential increases in this direction, then the electric field direction is in the opposite direction, that is, this is the direction of electric field. Electric field by definition are the directions of the electric lines of force which emanate from positive charges and terminate on negative charges, all right. And therefore phi, the direction in which phi increases and the direction in which E sets up are opposite to each other, and the exact relationship is E equal to minus d phi dx, the negative gradient of potential. This must be understood. That brings us to the concept of an electric field. Electric field, you see, we are mixing things up, defining one in terms of the other, then defining the other, and so on. This is a convenient way of refreshing memory, because all the absolute definitions are known to you. What is an electric field? An electric field is, well, first, existence. An electric field exists around a charge or a set of charges, all right. A charge or a set of charges, there exists an electric field. You could have, let us say, a sphere charged with, let us say, plus q, or you could have 2 spheres, one is plus q and the other is, let us say, minus q. Then whenever there is a charge around, there exists an electric field. Now the property of an electric field, the manifestation of an electric field is that if you put another charge nearby, it shall either be attracted or repelled in a specific direction. It shall move in a specific direction which shall indicate the direction of the electric field, and the amount of force experienced if this extra charge is a unit positive charge, that is 1 coulomb, then the force experienced will give you the value of the electric field, and the direction in which this force is exerted will give you the direction of the electric field. And therefore electric field is specified by 2 quantities, one is the magnitude and the other is the direction. So it is a vector quantity, all right. Now the charge need not, the set of charges or the charge which sets up an electric field need not be stationary, it could be moving. Now if the charges are moving, then in addition to electric field there also appears a magnetic field, all right. And if there is a magnetic field, then we define what is a quantity called magnetic flux density, and this we shall denote by B. B is also a vector, and the definition of magnetic flux density, or the unit of magnetic flux density, well, we shall not have much to do with magnetic flux density in the course on electronics. Maybe sometimes we shall be required to, but it is good to know that magnetic flux density is defined again in terms of the basic unit, basic quantity, which is a force, comes from Newton's second law of motion. It can be shown that the force experienced by a charge q moving with a velocity u, velocity is a vector quantity, moving with a velocity u in a magnetic field of flux density B is given by this. Force is equal to charge multiplied by scalar multiplication, q is a scalar, multiplied by the cross product of u and b. The cross product of u and b, the magnitude is product of the two magnitudes multiplied by sine of the angle between the two, and the direction is perpendicular to the plane containing u and b, following which rule? Right hand rule. All right. We will not go into more details of this, perhaps it shall be done a little later, and you will have much more to do with this in the course on Introduction to Electromechanical Energy Conversion if you do take that course. But let me point out a clever way of defining the magnetic flux density. Obviously, it shall be equal to the force exerted on a unit positive charge 1 coulomb moving at the rate of 1 meter per second. So that is how we define the magnetic flux density. You see, we have defined force in newtons is a absolute mechanical quantity. There is an absolute standard for this. There is a standard for meter, there is a standard for time. So meter per second is the velocity, this is in newtons, and we have already defined a coulomb, and therefore it becomes very convenient to give an unit to B, that is the magnetic flux density, and this is named after the Czechoslovakian, was it Czechoslovakian? No, I am not too sure. Gentleman Tesla, Nikolai Tesla. So a unit of magnetic flux density in the SI unit, System International, is a Tesla. Now let's go back to charge and voltage and energy. Well, the voltage at a point, considering the ground as reference, is obviously, let us put it this way, if you wish to move a charge dq, an elementary charge dq, through a potential difference of V, then the amount of work that is required to be done is V times dq. This is the amount of work required to be done, dW. All right. So dW is equal to V dq. In other words, V can be written as dW dq. This is the relation between voltage, energy and charge. V is dW dq. All right. And therefore, if you understand this, it is very easy to see that the power, which is the rate of change of energy dW dt, can be written as dW dq. How does Vi come? That is what I am showing, times dq dt, and dW dq is V and dq dt is I. So the power in electrical engineering is simply the product of voltage and currents. So volts amperes is the same as watts. All right. And if you want the energy W, energy by definition, power by definition is the rate of doing work. P is dW dt. So energy must be P dt, let us say from minus infinity to t. If you start at minus infinity to t, this is the total energy consumed by an electrical circuit, where, and this can be written as minus infinity to t Vi dt. Let us consider, yes.
So why do we start at minus infinity? Should be 0.
Why do you start at minus infinity? Okay. Let us take a capacitor and we charge it to a certain voltage, let us say capital V. All right. If we take the lower limit as 0, then you shall have to consider the initial voltage on the capacitor. That is, you have to do 0 to t plus the effect of the initial voltage, because initially also there is some energy in this. If we take minus infinity to t, then all initial conditions have been taken care of, and therefore we say from time immemorial, whatever the history the device or the electrical circuit may have gone through, we don't care. We simply multiply Vi and multiply by dt and integrate from minus infinity to t. There has to be a reference of time when you are considering an electrical circuit. If that reference is taken as 0, then you must see what was the condition of the circuit as 0 minus, because electrical circuits can store energy. They are dynamic devices. This is a dynamic phenomenon. They can store energy, they can dissipate energy, they can deliver energy, and therefore you must consider, it is safe to consider from minus infinity to the present time. We shall break up this integral to 0 to t plus the condition at 0 minus later on, all right, to take care of all that had happened between minus infinity and 0 minus, all right. Let us consider a simple resistance whose model, that is, we are considering the resistance in a range of environmental conditions such that the model is a pure resistance like this. We call this an ideal resistance, okay. Ideal, that is, it contains only resistance, nothing else. An ideal resistance, you know by Ohm's law, that if you plot V versus I, it shall be a straight line with a slope of R, V equal to IR, and therefore dV di shall be equal to R. Now this is an appropriate point to introduce another term, that is a term called linear. We shall consider all electrical devices in this course as linear. There are resistances which may not behave, which may not obey Ohm's law. There are resistances which may not obey Ohm's law. For example, a thermistor or an electrolyte. It may be such that it behaves, it obeys Ohm's law for a certain region and then it saturates like this. Such a resistor is called a nonlinear resistor. A resistor in which V is linearly proportional to I is called a linear resistor, and we shall always consider in this course linear resistors unless specified otherwise. We shall also consider nonlinear resistors a little later, but most of the resistors that we consider shall be linear. This is a good point to stop. Next time, in the next lecture, we will go to the other kinds of circuit elements and consider the implication of linearity in them. Thank you.